Hello, this is Mr. Rallison, and this video is to walk you through determining the features of a rational graph. It might get a little long. We have to find holes in the graph. We have to find vertical asymptotes. We have to find horizontal asymptotes, and then we have to find the x and the y intercepts. So let's start. This, by the way, this has a handout that accompanies it. So the first thing you're going to want to do when you're graphing anything is factor the denominator. So right now I am looking at this function right here, the first one. I'm going to factor the denominator. And so right now you have terms, you have three terms, but you can't cancel terms from the numerator and the denominator of fraction. You can only cancel factors. Factors are, if everything's multiplied together, then that's factored. And when it's not, then it's divided up into terms like this. So there's nothing we can do to the top, and we're not going to worry about the top yet because we're factoring the bottom. And we're looking for, that's an x squared, so we don't have to do anything special to that. We can just make that an x like that, and an x like that. And then we're looking for something that multiplies to -8 and adds up to +2. And so the factors in -8 that will add up to 2 are going to be what? It's going to be +4, right? And -2. So the first thing we're looking for when we look for the features of a rational graph is we're looking for where the denominator equals 0. So you've got two little expressions here, x plus 2 and x plus 4 and x minus 2. And if either one of those equals 0, that means the whole thing's going to equal 0, right? So basically, you have these two terms, this x plus 4 term. So you're going to say, well, if I have x plus 4 and that equals 0, what does x equal when this expression evaluates to 0? And you can see that that means that x equals -4. And if you have x minus 2 and you want to know where that equals 0, add 2 to both sides. You can see that that's at x equals 2. So the denominator is going to be 0 at x equals -4 or x equals 2. The top has just an x plus 2 on it. So there's nothing we can do there. There's nothing we can cancel out. We can't do anything further than that. So this graph tells us, the first thing it tells us is that we have vertical asymptote at x equals -4 and x equals 2. So I'm going to put those in. Oh, I got to change the mouse. There we go. There's our asymptotes. We'll see those when they get there. There's no hole in this graph because nothing can be canceled out. So what other features are we looking for? We don't have to calculate the x, y. We calculated the vertical asymptotes. Now we got to think about a horizontal asymptote. Where is the horizontal asymptote is actually not too bad to find. Basically, what you're looking at is when you're trying to find the horizontal asymptote, you're asking yourself what happens when x gets really, really big, because then the horizontal asymptotes happen as x goes to infinity. So there's rules in the sheet. What you're going to look for is just the term in the numerator and the denominator that has the highest order of magnitude, that has the highest exponent. So on the numerator on this one, we have x plus 2. So x has the highest exponent, just x equals 1, right? And then on the bottom, the highest exponent is the x squared. So we can get rid of that. So now we're just left with x over x squared. And the rule tells us, think about what happens when x gets really, really big. If there's no leading coefficients, or if the leading coefficients are the same, and well, in fact, anytime the exponent in the denominator is bigger than the exponent in the numerator, this thing's going to go to 0, right? Because what happens, just think about what happens if x equals 1,000. It's going to be 1,000 over 1,000 squared, which is a million, right? Did I get that right? Yeah. 1,000, 6 zeros, a million. What happens, and then it goes on from there. So it's going to get, as the denominator gets much bigger than the numerator, it's going to get close to 0. So we're going to have a horizontal asymptote, and I didn't actually add that in like I did this other one. So we're going to have a horizontal asymptote at y equals 0. And what else can we find here? Well, that's about it. And if you want to find out where those asymptotes are going to land, just plug in, an x value to the left and right of each of where those asymptotes are and calculate it. And then you'll find out whether those asymptotes are going to be a positive asymptote or a negative asymptote. So now I'm going to actually put that graph in there, and we'll see what comes out of that. So there we go. So we have an asymptote at x equals -4. So if I put a -5 in, you can't put a -4 in because it doesn't exist, right? But you can put a -5 in, and if I put a -5 into that expression, I would get something, right? I need to get my pointer back, my pen back here. I would get something, about right there, right? And then I would be able to tell that it's headed downward. And if I put in x equals -3, then 5, 4, 3, I'd get something right there, and I'd be able to tell it was headed upward. And then I would put in 1 to the left and the right of the other asymptote, and I would be able to see where those are all going. So the asymptotes basically kind of form the boundaries of what's going on. And then you just have to plug in a few numbers and maybe plug in a couple extra. You could see what's going on. But you kind of just have to do that once you got the asymptotes. But the asymptotes kind of form the walls. Now, it's important to note that the graph will never cross the vertical asymptote, but it can cross the horizontal asymptote, and we'll get to that in a moment. But first, let's just erase this and look at a couple more things. So there's the graph again. And you can see it's the exact same graph as this, right? It doesn't matter which one of those I activate. It's the exact same graph, right? All right, so that's x plus 2. And if you remember the denominator of this one factored into what? It factored into x plus 4 and x minus 2, right? So what if this equation had an x minus 2 on the top instead of an x plus 2? Well, let's go take a look at that now. So here we go. Let's cancel those out. And we'll slide up here because I just happen to have that graph right here. All right, so we'll go back in here, and the first thing we're going to do is factor the bottom, because that's going to tell us, oh my goodness, if my board starts acting up, I might scream. So we'll factor the bottom, because that's going to tell us the values we are not allowed to have. Because you can have a 0 on the top all you want, but you can't have a 0 on the bottom, okay? So this, we already factored it, and I'm just going to put it in here again. That is going to be x what? X plus 4 and x minus 2, right? And we said that the values of x that you are not allowed to have, you can't have a -4, because if you put a -4 into this factor, that will result in a 0 in the denominator. And you can't have a 2, because if you put a 2 into that factor, that will result in a 0 in the denominator. So those are both places you're not allowed to have certain values of x because they'll result in a 0 in the denominator. However, in this case, when we factor this thing out, we find out that we can actually algebraically cancel the x minus 2 factor, right? We've got an x minus 2 on the bottom and an x minus 2 on the top. So what does that do to the graph? It changes everything. Instead of there being an asymptote at x minus 2, now there's a hole. So let's take a look at it. It's the same graph, except that I have x minus 2 on the top now. So there we go. So we still notice we couldn't factor out the piece where this x minus x plus 4 is, right? So we still have our vertical asymptote at x equals negative 4 because we couldn't factor that out. But the piece that said, well, you can't have a 2 either because a 2, if you have x equal 2, you'll end up with a 0 in the denominator and that's not allowed. But because we can factor that out, that's not an asymptote. That ends up being a hole. And I could have sworn I had the hole in here, but evidently I don't. So I'm going to get here and we're going to just go over there. It's where x equals 2, right? So we'll just follow this around and you're going to see right where x equals 2, it's going to be undefined. And I thought I had, there it is, right there. Whoops. Woo. There you go. I get it. I got it. There it is. At x equals 2, y is undefined, right? So if you can cancel it out, it's undefined. If you can't, and we're talking about the zeros in the denominator, if you can cancel them out, it will be a hole in the graph. If you can't cancel it out, it will be a vertical asymptote. So once again, so here we have a hole at x equals 2. I should mark that there. Oh, that's not a pen. I need a pen. Once again, we have a hole at x equals 2. And we have a vertical asymptote at x equals negative 4. We have a horizontal asymptote at 0 again, because, let's just walk through that again. When we're looking for the horizontal asymptote, what we're doing is, excuse me, we're looking at only the highest order term on each in the numerator and the denominator. So x is the highest order term there, so we get rid of that. And x squared is the highest order term, so we get rid of that. Now we're just left with x over x squared. And we ask ourselves, what's going to happen when x gets really big in either direction, right? Because it's a squared term. So even if you're negative, it's still getting really big either way. So if x is 1,000, then x squared is going to be 1,000,000 and so on. So you can see that as x gets really, really big, this thing gets closer and closer to 0. So that's the horizontal asymptote. And then there is, we need to, the last two things we need to do are to find the x and the y intercepts. All right? So I'm going to erase that stuff. My board is working so much better than yesterday. It makes me very, very happy. So we need to find the x and the y intercepts, and that's the last piece of the thing. So the y-intercept, here's the y-intercept line right there, right? So the y-intercept is wherever x equals 0. So that's pretty easy to find. All you do is put a 0 in for x. So it's not an equal sign. So if you want to find out where y is when x equals 0, that's going to be 0 minus 2 over 0 squared plus 2 times 0. You can see how easy this is, right? Minus 8. So we're going to have our y-intercept at negative 2 over negative 8, which is actually just equal to 1/4, right? So I should be able to go to my pointer over there, and we should be able to go like this, and right there. There it is. Our y-intercept is 0, 0.25, which is 1/4. So for our y-intercept, we put 0 in for x, and we're done. Now, to get our x-intercept, we have to put 0 in for y. And we already found out on this one that we have a horizontal asymptote at x equals 0, so we're not going to be able to find one. But let's just kind of walk through it anyway. So we got x minus 2 on the top, and we had what? We had x plus 4 and x minus 2 on the bottom, right? And so our x minus 2's canceled out, so we are just left with, and I'll write it over here, 1 over x plus 4, and we want to find out where we're going to cross the x-axis, so we got to set y equal to 0, and then that's not actually solvable because you could multiply both sides by x plus 4, right, and then you get 0 times x plus 4 over there, but then that just equals, then you end up with 0 equals 1, which clearly does not exist, DNE, which you'll find later if you take calculus. That's actually a thing. I'm not making that up. DNE does not exist. So then you find out there's no horizontal asymptote. There's no x-axis. But you already knew that, because if there's a horizontal asymptote at 0, then there's going to be no x-intercept. Same thing with if it looks like there might be a hole somewhere, but there's also a vertical asymptote. The vertical asymptote's going to override the hole, okay? So let's just do a little bit more. I don't want to make this too long. That's the same graph right there. Okay, so now I've got a few things here, and we're just going to kind of look at them and say, okay, here's 1 over x plus 4. So is there going to be a horizontal or a vertical asymptote of any kind here? Well, so we're going to start, you can't factor the denominator, it's already a factor, right? And what we're looking at here, so we set the denominator equal to 0, x plus 4 equals 0, and we find out that at x minus, x equals negative, if that's going to evaluate to 0, that'll happen when x equals minus 4. And that's not cancelable, so we're going to assume that we have a vertical asymptote at x equals minus 4. And I'm going to draw that in like that. And then are we going to have a horizontal asymptote? There's no holes because there's nothing cancelable. So then are we going to have, let's see, we calculated the vertical asymptote. So now the horizontal asymptote, which we're going to look at the terms of the highest order, right? So that's just a 1, that's not a term. And so what's going to happen as x gets bigger and bigger and bigger? Well, it's going to get close to 0 again, right? So let me change color. So we're going to have a horizontal asymptote again at y equals 0. And then for our x and y intercepts, so we know we're not going to have a y-intercept because we're going to have horizontal asymptote at x equals 0, right? But let's just go through the process anyways. So to find our y-intercept, we take this function, right? And we put 0 in for x. So we've got our y-intercept is going to be at, I was going to make an at symbol, and then I ended up writing in cursive. Our y-intercept is going to, let's see, okay, so hang on, it's late in the day. So that's going to be y y equals negative 1/4. Yes. I can't believe I just got confused on that. So our y-intercept is going to be at negative 1/4. That's divided up into fifths. That's inconvenient. So it's going to be about right there somewhere. And then our x-intercept. So we're going to put 0 in for y and then solve for x. Can we do that? Again, we're going to, the only thing we can do there is multiply both sides by x minus 4. And that still leaves a 0 there, and you get 0 equals 1. So it doesn't exist, but we already know it because we determined the horizontal asymptote. So let's do that. There we go. I did something wrong. What did I do wrong? Oh. All right, I know what I did wrong. Because it's a transcribing error. How often do I do that? I apologize. Notice that I wrote it wrong. I put 1 over 0 minus 4, and it should have been 1 over 0 plus 4, right? So y equals 1/4, not minus 1/4. So there we go. Maybe you caught that ahead of me, and that would be great if you did. So we're just going to do like one more or so here. And let's just, what I want to do, I want to take a couple minutes and put some things in to the graph and see what's what about it. Calculating the holes and stuff, I think that's pretty clear. But what I want to do is just mess with horizontal and vertical asymptotes for a moment. The horizontal one, actually. So right here, remember, you have to look at the order of magnitude of the highest order term in the numerator and the denominator. And then if they're the same, then all you do is look at the coefficients. And if they're different, if the exponent on the numerator is higher than the denominator, there's no horizontal asymptote. And if the exponent on the denominator is bigger, that's going to just make the denominator grow really fast. So that's going to give you a horizontal asymptote of 0. So here we have x squared over x squared, which is just 1, right? So what happens, so they have the same exponent. What happens if I put, where's my keyboard? Here it is. What happens if I put a 2 in there? What's going to happen? That's going to move that horizontal asymptote up to 2. There it is. And what if I have a 3 there? That's going to move it down to 2/3, because again, x squared and x squared, they're going to end up canceling each other out, right? And you're just going to end up with 2/3. So that's that. Now, that's just the graph of the function, right? But what if I have a bunch of other gobbledygook here? That's a technical term. What if I have 3x squared plus 4x minus 7 on the bottom? Okay, so that's a weird graph, right? But you'll notice that it still actually has a horizontal asymptote at 2/3. What if I put some more gobbledygook in there and say that's going to be minus 17x plus 6? All right, so that's that, and we still have, obviously the graph has radically changed. But if we zoom out a ways to see what's going on, you can tell that no matter what we do to this part, all that's going to happen is this part over here. Oops, sorry about that. The part that has the highest coefficient is going to take over. That's always going to happen. So let's erase that. And now, what happens if I make this 3 over change that. Now what's going to happen, as soon as I change that exponent to 3, we're not going to have a horizontal asymptote anymore because the numerator is going to take over the function. There it goes. See, no, I mean, it's crazy looking function, but there's vertical asymptotes, which we could go find. By the way, this is an important time to note. The vertical asymptotes are created by zeros on the bottom that can't be canceled out. This new denominator there is not factorable by normal means. You have to use a quadratic equation, but you can still find the 2 zeros, and you can see the 2 vertical asymptotes there. So, but if I make this bigger or whatever, you can see that the numerator, because it has a higher exponent, a higher order of magnitude, just takes over the function. And there is no horizontal asymptote. But let me take that back to 2. All right, so now our asymptote's back to 2/3. Now what happens if I make the exponent bigger on the bottom? If the exponent's bigger on the bottom grows faster than the top, and that moves our asymptote to 0. That's all that happens. And it doesn't matter if it's like giant. It just goes to 0 faster if it's giant. Now, just to show you that it still will be an asymptote at 2/3, regardless of the exponent, I'm just going to change that to a 6 too. And there it is. See? X to the 6 over x to the 6 is just 2/3. And the other terms, the 18x and 6 and 4x and minus 7, in terms of their weight in the function, they basically disappear. So the last thing is I want to just show you that you can have a horizontal, the function can't cross, hang on, let me get what I'm trying to say straight. The function cannot cross a vertical asymptote, but it can oscillate back and forth. It can cross back and forth over a horizontal asymptote. And a sine function is a great example. So there is, I'm going to move in. This is this function sine x over x. And remember, sine oscillates. So the top of this, the numerator on this particular function oscillates between 1 and -1. And the denominator of the function simply gets bigger or smaller as x, does its thing. And so you can see that in this case, there absolutely is a horizontal asymptote at 0. It's getting closer and closer to 0, but it's wavering back and forth over 0. And you can find that on horizontal asymptotes, but never on vertical asymptotes. I'm going to just put a number in here, and I don't even, let's see. So that just makes it bigger. And what happens if I put like a 3 in there? So there we go. So it doesn't actually really change anything because that sine function still is just oscillating between 1 and -1. That's all. That's a long video. Hopefully that's helpful. Bye.